Hi everyone and welcome back. This is Miguel Alfonso Mendez from the Von Karman Institute, and in this video we will talk about how to use the constrained RBF formalism to compute pressure fields from image velocimetry. This is the fourth video in the mini course covering the theoretical background of SPICY. In the previous videos we introduced the idea of constrained and penalized RBF regression and how to use it for regression of velocity fields. Now in this video we will focus on the pressure computation. As we will see, this is a very challenging problem. In SPICY, at least for the moment, we only focus on incompressible flows. In these flows, the pressure can be linked to the velocity fields in two ways. The first way is from the Navier-Stokes equations. These link the pressure gradient, which is the term you see here on the left, to the material acceleration. So here you have the material derivative of the velocity field, the viscous diffusion, so here you have the Laplacian of the velocity fields, and the gravitational acceleration. Keep in mind we're using here a classic notation in fluid mechanics, so rho is the density of the fluid, mu is the dynamic viscosity of the fluid, and g is the gravitational acceleration. Now the second link that we can build from pressure and velocity is through the pressure Poisson equation, and this is obtained by taking the divergence of the first equation. The reason why this is interesting is that for an incompressible flow, continuity says that the divergence of the velocity field is to be equal to 0. So when we take the divergence of this equation, we note that the time the derivative that is inside the material derivative can be swapped with the divergence operator, and so it is easy to show that it can be removed. So this equation per se does not depend on time. Of course, it doesn't mean that the pressure is no longer depending on time, because we still have to include the boundary conditions, and we will see it will come there. But at least the equation itself does not depend on time. Now, there are the numerical techniques that you normally use to solve these two equations are very different, and in this work we will only focus on the second one, because SPICY is working with the second with the pressure Poisson equation. When we solve this equation, we usually do it using two kinds of boundary conditions. These are the Dirichlet boundary conditions and the Neumann boundary conditions. In the Dirichlet boundary conditions, we will impose the value of the pressure at some specific points, which we denote as xd, and we denote as pd the value of pressure which we are imposing in those points. In the Neumann conditions, we impose a certain value for the projection of the pressure gradient along a certain direction. This direction, which I denote here as NN, is usually the normal direction. This is the direction normal to the surface on which we're going to introduce this condition. When this is a wall, what is typically done in CFD is to set this quantity equal to 0, because if in this wall we have the development of a boundary layer, we know that in boundary layers usually the pressure gradient along the normal direction, normal with respect to the flow, is equal to 0. But this is not, strictly speaking, valid in many other cases. So this is why in SPICY we leave the right hand side term almost as it is, except for one simplification, and in particular we simplify the time derivative which is inside the material derivative, as we will see shortly, because it is usually very difficult to measure these quantities experimentally. Now, a way to avoid this problem, let's say, is to focus on statistics, so on time averaged pressure fields. So let's say we have carried out measurements using PTV or PIV of a statistically stationary flow, and we decompose this using the Reynolds decomposition into a mean flow and some fluctuations. Here the bar denotes average, and the prime denotes the fluctuations. Now this is the natural setting in the so-called Reynolds average Navier-Stokes formulation of turbulent flows. If we introduce this decomposition with the bar and the fluctuation into the Navier-Stokes equation, and then we take the average, we obtain the so-called RANS, the Reynolds average Navier-Stokes equations. This looks a lot like the Navier-Stokes equation which you've seen before, with the only difference being the presence of the bars on top of the variables, and plus an extra term, which is the one that you see here on the right, which arises from the averaging operation on the nonlinear terms which are in the material derivative. These terms appear within a divergence operator and are known as the Reynolds stresses. They can be computed experimentally, especially from PTV, and Manuel Ratz will talk more about this in the last video of this course. But assuming that we have found these Reynolds stresses and we have also a good regression using radial basis function of these stresses, then we can take the easily the divergence, or we can easily compute this term in the equation. And if we take now the divergence of this Reynolds average Navier-Stokes equation and we use again the continuity equation, we arrive at the pressure Poisson equation for the average pressure field. So in this case, in addition to the previous term which we have already seen, we will have the divergence of the Reynolds stresses. Now, the first application of this formalism, in particular using radial basis function, was presented in this paper in 2022 at the International Symposium on Applications of Laser and Image Techniques to Fluid Mechanics. But it is currently under development and is not yet released in the current version of SPICY. It's coming soon, and you will learn more about this application after in the presentation given by Manuel Ratz at the end of this course. Now I want to show you how the pressure Poisson equation is handled in SPICY, and to do that I consider a laminar 2D case. So here is our pressure Poisson equation with the right hand side written for the 2D problem. Note that this equation is non-linear in the velocity, but is linear in the pressure. And in SPICY we like to deal mostly with linear problems, so the pressure computation is enabled once you have carried out the velocity regression. If you have the velocity regression, you can analytically compute the right hand side and then focus on the linear problem. So to compute this right hand side using the RBFs, you will need just a bunch of matrix vector multiplications and squares. Here all these operations are meant to be entry by entry, so this symbol here denotes a sure product, so element by element, and this square is also seen in terms of element by element. So the result of this operation would be a vector, which we call S, that is the source. And in SPICY you will be able to compute this in just one line of code once the velocity regression is available. Once you have this right hand side of the equation, you can proceed as we've seen in the first video. So we will look for a solution of the pressure in terms of an RBF approximation. So we will have the usual matrix vector multiplication, where we will have our basis of our set of RBF bases. And because the problem is linear with respect to this solution, when we introduce it into the equation, the Laplace operator will just act on the basis. And so we will have our linear problem, which is going to be identical to the previous, with the only difference being that the columns of this operator L, instead of having the basis, will have the Laplacian of that basis. So our solving the Poisson equation for us means minimizing the residual of this equation, which we will write, which will first write in terms of L2 norm of this residual vector, and we will try to make this as small as possible. Hopefully it will be 0, but in practice it will never be 0. There will be a certain error there. So in terms of, let's say in the machine learning terminology, we will consider S, the sources, as our target data, and the problem now is converted into a classic supervised learning problem. Now, in the same way we did for the velocity regression, for the pressure computation we can also impose the Dirichlet and Neumann conditions as a constraint or as a penalties, but we will mostly do it as a constraint. Now, because of the challenges which I told you concerning the Neumann conditions, the general advice, rule of thumb which I can give is to try to avoid them as much as possible, in the sense that wherever you have Dirichlet conditions, you should really use them. So you can have Dirichlet conditions because during your PIV or PTV experiment you had pressure taps or some pressure measurement in some points, or it can also happen that you have some regions of the flow where the flow is nearly irrotational, and so there you can use the Bernoulli equation to have an educated guess of what the pressure should be there. Whatever you should do whatever you can do to impose as many Dirichlet boundary conditions as possible. When not possible, then you have the Neumann conditions, and as we have seen in SPICY, they would be implemented from the projection of the pressure gradient. And here again I stress again the fact that we will not have the time-dependent problem, the time-dependent term. So if we want to use SPICY to deal with instantaneous fields and we don't have time derivatives, the time derivative terms is important on the boundaries, then of course this will SPICY will face big problems there. Once you have introduced these conditions, you arrive at the canonical system, which we have seen already several times in this course. We will have a block-like linear system where we have a block that contains all the terms that were linked to the weights in the cost function plus our usual Tikhonov regularization. We will have a block term that contains the matrices for the constraints. On the right hand side we have the usual projection on the target data of our operator, the constraints that we are setting, and our unknown as usual are the weights of our expansion and the vector of Lagrange multipliers. Note that this is now a scalar problem, so computationally speaking this is usually much cheaper than the velocity regression. Okay, so now that you've seen how to construct this canonical system also for the pressure, you have already seen it for the velocity regression, so the last piece of the puzzle is to see how SPICY solves this system, and this will be discussed in the last video of this mini course covering the theory of SPICY. So I hope that you have learned something, and I look forward to seeing you in the next video.